All right. Hi, everyone. My name is Darren. My pronouns are he and him, and I'm from the style team in Sydney.
Hi, my name is Naina. I'm also from the style team in Sydney, and my pronouns are she and her.
Cool. And today we're going to talk about an exciting project that we've been working on for the past 6 months. But first, let's begin with some background. As you know, CSS allows us to describe how elements on a web page should look. For example, here we have a CSS rule that makes text red and gives it an underline. And obviously, you can apply that to a div element, and it will have the correct appearance. But where does Blink actually store this style information for an element? How does Blink remember that this div has red underlined text and another div has a blue text, for example? And the answer lies in a class called computer style. The idea is that in most cases, every element has an instance of this computer style class, and this will store the style information. For example, we would have methods for getting and setting the color. We would have getters and setters for the text decoration, and basically every other CSS property. I'm oversimplifying things a bit, but you get the point. We also store some internal style related information that aren't CSS properties, but are needed by paint or layout. For example, whether an element is affected by hover. So I'm showing you a small example with only 2 CSS properties, but Blink actually implements hundreds of CSS properties. So you can imagine that this file will get huge. In fact, here's a video.
Oh, actually, computed file.
Of, sorry?
Yeah.
This is a video of Naina scrolling through the header file for computer style. And as you can see, it's quite big. And the key point here is that most of this code is actually boilerplate that you like the getters and setters that you saw before.
Can this be my screensaver?
Sure.
Coming to a screen near you.
Now you might ask, why is having so much boilerplate bad? Well, the style team has a lot of cool ideas for experimenting with computer style. We have a lot of cool ideas. I want to rapidly prototype them, try them out, and get results. But the huge amount of boilerplate makes this very prohibitive. Like imagine trying to refactor this code by hand, taking a whole week, getting it to compile, and then finding that your experiment doesn't really do anything, doesn't really help. So it's just not practical, which is why. So basically, the key goal here is we want to quickly allow quick refactors without having to worry about the complexities of computer style, without having to manually change thousands of lines of C++ code when you can, And that's why a year ago, we embarked on Project Clockwork, which is an attempt to fix this problem. Speaking of which, happy birthday, Clockwork.
I'm supposed to make a noise. I'm really sorry here to. Okay.
So the project was actually started by Sasha Morrissey, who is also on the style team in Sydney, but she handed over the project to us about 6 months ago. All right, let's see how we tackle the problem. And the idea behind Clockwork is actually quite simple. We just generate the boilerplate code instead of handwriting it. More specifically, we have a JSON file that has various metadata for each of the CSS properties. At compile time, a Python script will actually read this JSON file, do some processing, and generate the correct C++ code for parts of computer style, basically all the boilerplate. And this means that when we do experiments, instead of changing 1,000 lines of C++ code manually, you can just change maybe 10 lines of Python, and the generated code will be correct. All right, so what does this JSON file actually look like? Here's an example with the color property. So one thing to keep in mind is that different CSS properties actually have very different interfaces. So we just categorized CSS properties into what's called field templates. So here, color has the field template external, which is saying that the color property is represented by a C++ class called color, and that color class lives in the file platform graphics color.h. And we also specify that the initial value for color is black. So then at compile time, a Python script will read through this file, see this color property, and generate some code that looks like this for computer style. So we have a static method to represent the initial value for color. We have the getters and setters that you saw before, and we also generate the declaration for the color property. Here's another example with the float CSS property. So here, float is a what's called a keyword property, field template keyword. And I was just saying that float can be either none, left, or right. You can take on one of those values, and the default value here is none. So looking at the generated code, we still have the initial getters and setters, but because this is a keyword property, we can also generate an enum with the valid keywords as values. And for that extra icing on the cake, we actually can automatically calculate how many bits it takes to actually store this value, and that allows us to efficiently pack float as a bit field. So we added this metadata for every CSS property and wrote a generator that generates computer style, most of computer style. In the process, we removed almost 5,000 lines of boilerplate source code. Along the way, we found some bugs in the handwritten code that were mostly caused by typos. I'll get to that later. And most importantly, this allowed experimental refactors of computer style, which we'll see later. But not everything was easy. Our biggest challenge was that some getters and setters had special behavior. For example, the opacity property, the setter for the opacity property needs to clamp the value between 0 and 1, because opacity can only be between 0 and 1. And obviously, the generator setter doesn't do that, doesn't know about this constraint. So when we encounter these scenarios, we sort of have to make a design decision. Should we modify the generator to be able to generate such code, or should we just leave the code, the boilerplate handwritten? And in this case, we left the opacity setter to be handwritten. But in another case, there was a bunch of CSS properties that were stored as pointers. And in those cases, we decided to make a new field template just for these pointers, and mainly because there's just quite a few of them, and we felt that it's worth doing that. Another challenge was that computer style liked to store things as a single class, related properties as a single class. For example, there was so all the border related properties were stored as part of a single class called border data. But border is actually a shorthand property. It's not a CSS longhand property. So our generator couldn't handle that. And then I did a lot of refactoring work on computer style to actually split out into individual properties. And finally, as we were comparing, as I mentioned before, comparing the generated code with the handwritten code, we found some weird discrepancies. Like in the handwritten code, there was a case where the copy constructor for class was missing a data member. And we weren't sure if that was intentional or whether it was someone just missed it. And after emailing around, turns out it was a typo, they just missed it. But our automatically generated copy constructors don't have this problem. Cool. So I've talked about our work in generating computer style, but the real benefits come from enabling the experiments and refactors that I talked about earlier. So I'll hand over to Naina, who will first talk about how computer style is structured internally and how that inspired an experiment made possible through Clockwork.
Right. So before we can actually talk about experiments, like Darren mentioned, let's first see how computer style is structured. Computer style isn't exactly a dumping ground for all CSS properties. They aren't directly stored in the computer style class. They're actually stored on children classes that are groups of properties grouped together. So for example, style surround data is a group stored on computer style, which has information that the layout team finds important, such as margin, border, padding, etc. In this particular case, the groupings made sense. But then there's other cases where the groupings make zero sense. And rare non-inherited data, which is the largest group on computer style, is one of them. It has about 93 properties, rare, right? 57 further fields, which are all supposed to be rare. But when an intern that Darren and I have been hosting looked into this, he found that the opacity property was stored on this rare group. And go figure, opacity is used by 80% of page loads as determined by Chrome status. Rare, right? Some groupings did not make sense, and some groupings were just plain huge. And this was a challenge that we had to further deal with then. And now, before we could actually perform any of our experiments, which was our lofty goal, we had a few roadblocks because of the way all of these properties were grouped together. all functions on computer style depended on a property being on a certain group, and that's how they were accessed. They went computed style, styles around data, border color, etc. And this meant that we couldn't exactly play around with this. Diffing functions, which are used to compare to computed styles to further invalidate style, were one very large case that really depended on a property being on a specific group. So we had to go back, really rethink how our generator worked and allow for us to be able to change the way a property is grouped. Eventually, we were able to just go into the JSON file, and here's an example of how we changed the way the height property is stored. It was stored on the box group, and we stored it on an arbitrary group called E, which was stored on D, C, B, A, etc. Our generator handles this by generating all the class declarations of class E, D, C, etc. It then goes and changes the way the property is accessed within all the generated files. So you can see it move from accessing it through box to A, B, C, D, E, etc. It also changed all the diffing functions to allow us to access it properly via that group. Now that we are actually able to play around with the groups, one experiment that we wanted to carry out was understanding how much memory the style team was taking up with compared to other objects, such as node and layout objects, which are objects we work with on a daily basis. Before actually generating computer style, we'd have to go and figure out how to change the way all the groups are created, to add printf so that we could see when they're created, when they're destroyed, etc., which would have taken a very large amount of menial labor. However, because of our Python generator, we were just able to generate these print statements easily and then just write Python scripts to analyze that complete deluge of prints. So what we did was we looked at some of the top 25 properties that Blink is interested in. These were determined by the Blink style top 25 metrics. And we were able to analyze how much memory computer style and its subgroups take up with comparison to node and layout objects. Now, as you can see, computer style is the sky blue object across the top 25 properties, and across the board, it takes up a large amount of memory, not just it, but its subgroups, etc. And that's being compared to node and layout object, which take up a lesser amount of memory. After having performed this analysis, we thought, okay, let's try and work through this. Let's try and get some memory gains here. And so we've had an amazing intern over the past 3 months. Unfortunately, this isn't being live streamed, so he can't exactly, don't wave to him, he's not there. But yeah, he's been working over the past 3 months on optimizing grouping for computer style. And the intention here was that we want to be able to allow computer style groups and allow the properties in computer style to change with the way the web pages change. And so he was able to factor in real world user statistics from Chrome status to change the way properties are grouped, so that rare properties actually are stored together in a rare group, which aren't allocated that frequently, and more frequently those properties are then allocated separately. As a result of this very small experiment, he was able to get a 1.08% memory gain on the top 10 websites on memory on mobile platforms already, just by this very small experiment. And this just goes to show that yes, this has allowed us to experiment with this, and we hope we can. If you have any ideas, we hope we can get more memory gains and even more speed gains potentially because of generating computer style. And just to quickly wrap up, before we actually started on this work, computer style was a beast of a class. It was 7,000 lines of code, a pain to maintain, a pain to even work around. But now it's modifiable by JSON, and we hope that not only our team, but other teams can also give us ideas or take the initiative themselves to experiment with it. We also have been editing CSS properties.json5 and computer style extra fields.json5 heavily. So if you think that it's unintuitive, or if you have any feedback on the way that's structured, do give it to us. We're hoping, we want to give this some cool time. We want cooling time so we can get your ideas and get your feedback on this. And what can we say except you're welcome? You don't thank people. Sorry, I'm not very funny. But yeah, if you have any questions, that's it.
Sorry, I do. Sorry, I just want to ask a very stupid question. I wonder, have you maybe using protobuffer, since you kind of get the setter and getter for free?
Yeah. So protocol buffers. Yeah. So our stuff is sort of like a hand-rolled protocol buffer.
Right.
Protocol buffers is probably too complicated for our use cases, and there's like special cases in style that can't really use protocol buffers. Unless we sort of fold protocol buffers and have
right.
Another thing interesting about protocol buffers is you cannot have more than 2048 members in a single message if you wanted to compile for Java. I don't know if you need to compile it for Java. Yeah, interesting cases that we can.
Yeah, there's a story in there somewhere.
Have you seen any change in build times from this?
I don't believe so, because we technically just regenerated the original handwritten code.
Okay.
We did make a silly mistake and started importing computer style everywhere, which did increase build times just generally, but that wasn't as a result of this project. It was just,
That was a bug.
that was, yeah, our bad.
So automatically generating all the boilerplate is awesome and makes things a lot easier. However, it has a slight downside, is that it's a lot harder to trace some of the calls.
Yeah.
And especially many of these types now are not actually defined in C code anywhere.
Yeah.
Do you have any ideas for ways to make that easier to work with? Like when you encounter a class or an enum type, maybe we can have a special prefix or something to indicate that this is a generated one and you need to look in a JSON file rather than try to find a corresponding header file for it.
Yeah, absolutely. Yeah.
I think that's a good idea, because E just means that people will be looking in computer style constants, and I know you've done that before. And I know that I was looking at the file with Ian, and it was a bit counterintuitive in the way things are named, etc. Yes, we should probably indicate very clearly where things are generated. Because you shouldn't have to go to computerstyle.h and look at the comment right above it that says, oh, this is some of it may be in the generated code. That's why it's intuitive to us. It's intuitive to the style team, but yeah, you're right. There should be some marking.
Yeah, like something as simple as a generated prefix or something would go a very long way.
Yeah, agreed.
I definitely agree with that. Something. Yeah.
Doesn't code search follow the generated code as well? Doesn't it?
I've never got that to
Question,
work.
sorry?
Well, code search will index the generated code.
Yeah. So I think you can just keep that.
If you don't use code search,
If you use it just normal, and I mean, I only use code search when I'm actually looking outside my own code base, like core CSS, and I'll look at code search.
That's what I think this is intended for, right? Because if you go, you do it
Generated
probably
file.
not.
Yes, but that's, yes, but it's better to make it easier. I would agree that it's better for it to just be very obvious in the start, especially if you're experimenting with it. And then for our team, we understand intuitively but if others are experimenting with it and we do want them to encourage them to do so, the easier we can make it for them, the more likely they are to do so.
It's helpful to understand what's the original version. It's generated code, so you can change it.
Another question. So you mentioned that you split out many properties from these large structures you used before. Have you seen any performance implications for that other than memory?
So speed-wise, we haven't seen a difference. Memory-wise is the only way we've seen that small gain over there. We do have a few more ideas in the way we're going to work, in the way still Mindox does. We still have a few more ideas, but we are trying to have more conversations in the way, we aren't the only customers of CSS properties or JSON, so we want to be, before we do anything more lofty, we do want to talk to the other style team members, talk to the other teams as well, just to make sure that what we want doesn't directly conflict with what they want. I know that initial functions for initial getters for all properties is something that people do want to move outside of computed style, and that's a discussion we again need to have. So we're waiting on these discussions to get a bit resolved before we can do anything more crazy. That's the only one we've done.
It looked like computer style was much bigger than the node and layout object combined. What are the fundamentals there? What is it that each layout editor has one computer style object and all of those are just huge and full of zeros everywhere? And what a kind of, can this be made 10 times better, or what? How much room for improvement is there?
That's a good question. I mean, before style sharing, yes, not necessarily every element had a computer style associated with it or via its layout object. But yeah, I mean, now because we killed style sharing, yes, there are more computer style objects being passed around. Yeah, we probably I don't know the internals of layout, so I can't really comment on the relativeness of things. But yes, we probably should figure out how to get computer style a little bit more fast. It's not full of zeros, but it is usually full of initial values on like really basic websites as well.
It sounded like there was a thing called rare rare what? I mean, like something like rare no data, but rare what computer style? Have you tried to group these groupings? Have you tried to find the grouping that is results in the least frequent? You could kind of put the 50% of the stuff in some other group and just compute which group of properties are supposed to go there, and then I guess memory cut in half.
Yeah, that's an interesting idea. That actually builds upon an idea somebody else mentioned. I believe Ian mentioned it. Don't quote me on that. Was that we cut up computer style into properties that are required by each pipeline. So cut it up into properties that are needed by layout, and then cut it up by properties that are needed in paint. And then hopefully, if we don't, and that will also help further memory gains, etc. Once we do have projects like layout ng, etc. So yeah, we haven't thought that crazy, but I think that's a great idea. Like cutting down computer style into actually really rare and just not having those at all, and then having the really frequently used properties. I think that's an interesting idea that we should probably talk through more, brainstorm or work later.
One constraint to what Naina talked about, the idea that Naina talked about, like having different computer styles for different parts of the pipeline, is that computer style is quite big in terms of binary size as well. So if you have like maybe 3 or 4 different types of computer style in the code base, it's hard to maintain, and it increases binary size by a lot.
Did you say we killed style sharing?
We did kill style sharing.
Interesting.
Was that a memory regression then?
There was no memory regression. There was a memory regression on our micro benchmarks, yes, because all of them were literally using free computer style objects, default computer style objects. We didn't see any memory regression on real world sites though. And we're currently without style sharing in beta.
Isn't that very surprising?
Elliot has an entire doc about why it's not surprising, actually. I can share that with people, but yeah, he did a bunch of analysis, and then everyone thought that yes, style sharing was hindering a lot of other projects that we wanted to take on. I personally had a lot of difficulty even trying to get my head around it when I was trying to split up style resolution and layout tree construction. I know that other people have had those problems as well. Might be because I'm junior, but yeah, it was just from my own experience, it was starting to get a bit finicky and insane. Just a lot of if statements up and down.
For the newcomers, what was style sharing?
Style sharing is when you would detect if two elements potentially have the same IDs, classes, selectors, etc. apply to it, and they just share a computer style object instead of having 2 separate computer style objects attached to them.
Okay. So you don't really compare styles themselves, just compare the collection.
Yeah.
Okay.
There's a lot of special cases.
Yeah, which invalidated, which means we weren't actually using it that often.
Yeah.
And yes, Mozilla launched quantum situation of style sharing, but we don't have proof out there.
The memory chart was before Clockwork, right? Is there a chart after Clockwork? No,
the background.
Oh, sorry.
Computer style.
This one.
This one is before Clockwork or after Clockwork?
This is we made this after Clockwork, actually.
After?
Yes. Okay. We had a bar graph before Clockwork, but it was incredibly counterintuitive to understand. And so while making these slides, we're like, we should make this more easy to understand.
Okay.
But yeah, we put we should potentially look at trying to revert all those changes and seeing how before and after Clockwork.
So I thought this was the motivation for Clockwork. This indicates we need more work than
the graph was the graph was the same kind. This graph was coincidentally just produced after Clockwork was actually done. But I still see that.
Why Clockwork?
Why Clockwork? Why Sasha?
My interpretation of Clockwork, one of the side benefits of doing Clockwork is that the style team will be able to understand the inner workings of computer style better. And like if computer style really complicated objects, it's like a Clockwork.
We didn't name the project.
Yeah, so we're trying very hard to explain it, but I have no idea.
That's the explanation you're going with, right? That was not our idea.
I heard project teams are supposed to be incomprehensible. Seems like the default.
My project.
Can you talk about fonts?
Yeah, but I came late, so I don't know. So one idea I had is lots of if you have all these completed style objects, they also contain, or that I always need to read the code again to get it right, but like they also produce a lot of font description objects, right? So we have font description objects on every node. Not all of them contain text, but we have this explosion of font description objects. And as soon as we start doing measurements with them, we need to break them down. And in the end, you end up on a page with only like something 10 to 20 really used fonts. Or like the font description objects, even if you have thousands of them at some stage, the actual sort of unique ones are like about 20. So
are they still copies? Are they still copies?
Yes.
Yeah. So they're still copies, and I've been thinking about ideas of what we could do there, and I'm willing to travel to Australia to think about what we could do. Maybe resolve fonts earlier, or somehow break this down and come to the unique number of fonts earlier. Of course, if you do font matching for every node that doesn't even have text in it, that doesn't make sense. That's too much work. But we might not need thousands of them, only to have sort of complicated font caching in place to bring them down to actually like a handful of used ones. But yeah, I'd like to explore ideas. I'm not too familiar with how all these objects get created. I know sort of the part where they get used in font matching and brought down to a couple of font platform data objects that we then in the end use for layout and painting. But maybe we can find a balance to bring this down, because font description objects are relatively large, and they contain a lot of, also as you say, like similar as for computed style, they contain a lot of default values, which we might not all need to have in memory.
I think that's a fair conversation to have, definitely. You should come to Sydney.
And yeah, so we did some profiling at first on speed, and it turns out a lot of time, a non-trivial amount of time was actually spent in copying those font objects, and it was because when an element tries to copy another element's computer style for inheritance or whatever, it sort of shares. It initially shares all of its subgroups. So like red non-inherited data, red inherited data, they're all shared. And then when you try to set a particular property in that computer style, it then does a copy. So then we saw there was like a lot of font copying in the profiles, which shows that like maybe font was in the wrong group. It was wrong, it was in the wrong subgroup, and we played around with that, making the actual font, the group that font was in actually smaller. But I don't have any concrete data.
So that's one step, but maybe we don't even need copies of this. So if we resolve it earlier, or if we, I don't know, if we create a hash key for it and only keep this around, or some other way, then we might not have this big font description blobs everywhere.
If you pre-pawn font. I think, yeah, if you can move font resolution up a little bit, that will definitely help with things.
Yes, but we should avoid doing it for elements that
don't have
never
have to happen.
Is all style in computed style, or is there anything that's computed when it's needed? Like, so Presto, the engine in Opera, didn't actually have computed style; it just calculated it when it needed it. Is everything computed whether or not it's needed and just stored, or is there anything currently that's kind of computed when it's needed?
Everything is computed by, when you go into the style resolution process, if you make a completely new computer style object, all this.
So style recalc basically pushes everything into computer style, and that's all you need to look at.
And then you pass that down to the layout team and then the paint project.
Yeah, I thought the same thing. Like sometimes you might just not want to store properties and just compute them dynamically if you knew your parent style.
Wouldn't you have to reparse the CSS over and over again?
No. Well, if it's inherited, wouldn't you have the pointer to your inherited style? Oh, maybe, yeah.
We compute and share the instance between two different computer styles, so we're not wasting that much, I think. But as they explained, we group them. So if we have different opacity, we have all other fields needs to copy.
Yeah.
There was an idea which was like involving a dynamic computer style. So currently all the fields are they're statically assigned to a group, subgroup, right? I compile that. My idea was sort of just basically store property IDs and the values in like basically a vector, and then basically. If the value is initial, currently, if the value is like initial, then you still pay the cost of allocating it. Whereas with the vector, you just don't store it at all.
Yeah.
And if you want to look up a property, you basically scan through a vector. And if the vector is small enough, that's quite fast. That was another idea. And like with this sort of Python generator thing, it's definitely easier to try this out. So,
yeah, I think the basic idea is like, wow, we're computing a whole lot of stuff we don't use very much and that we store around. So if there's any way around it.
Yes. It would definitely reduce memory.
We're on time. I mean, we're a minute over time, but thank you for your questions and your feedback. Hopefully we've written it all down.